in the middle of nowhere. We can't just end up doing nothing. We have to have a path. So I'm filling up all these gaps. Don't worry about that bottom bit at the moment.
Does the color of that matter?
No, because it's the same copper underneath. Right. Is anything happening anymore? No, that the plastic doesn't conduct anything. Is that working? Please tell me.
Switch.
Switch!
Switch. The others two.
The others too, this one?
Yeah. But it's not still like connected from that.
Okay.
Right.
Yes. Yes, 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 yes. Good. Power, not a lot. You need more candy. Better?
Yeah.
Okay. So now I'm actually on 9 volts. So you need a certain amount of energy. You need a circuit that is continuous, conducting path. So there's metal connecting every bit here in the switch. The 2 bits of metal have just been pushed together. Now they're apart. Okay, so there's a continual loop along here, and then there's a component where the people who bought the sweets, who've got the energy, they're doing some sort of activity. They're doing a job. They're not people, they're electrons. They are hitting the wire inside the lamp, and they are producing light. Not a lot of heat energy because it's energy saving, so they're producing light. So we get the energy from the voltage supply to move around the circuit, and we can do a job. Okay, any questions so far?
How does this work?
What is this? What is this thing here in our circuit?
Sparks.
Sparks? Well, it will do. This is our safety device. This is our fuse. Okay, now what does a fuse do? Blows up. No,
Melts.
it melts. If we didn't have a fuse, it is possible other bits of the circuit are far more likely to blow up. The fuse is a protective device that stops the rest of the circuit from getting damaged. Now, I'm hoping this will work. It won't. Okay, my sweet shop here is just like a little Sally. It can't produce enough energy to blow that fuse. Okay, I need a Futzer factory for that. Or I need to have a problem with the circuit. So my circuit, for instance, instead of coming out the sweet shop and going around and doing all that activity, there's a short circuit. So there's a short route. Like that. Okay? So that would then protect everything else that you've got. And in very, very old houses, the fuse wire simply was a wire that you put between 2 clips. Now it's magnetic and it is resettable. And it is very, very, very cheap to replace. Okay, so let's replace that fuse. And when you are setting up fuses in circuits, the fuse is normally rated in a particular way, a size of fuse. First of all, the physical size, so it fits in the right place, but then it's got to be a certain size, like those ceramic fuses. You've got the pink and you've got the blue, and it depends on the current that goes through. Now, we've not used the word current before, but you all know about electric current because it's what goes around the circuit. So we've got the energy here, we've got the people carrying the energy around doing the jobs. Yeah. Now the people are like the electrons. So what's the current? F-L-O-W-R-R-E-N-T, Virta, the flow. Well, the current is actually the number of electrons per second past a particular point. Number of electrons, we've got to count. Yeah, we have to measure it. The current is measured in amps or amperes. That's what these gaps are for. I have a current measuring meter, a multimeter. So these are actually quite complicated. Most people hate them because there's all sorts of different things they could be measuring. But you can get these for about 10 euros, whereas ammeters, which only measure current, are about 30 euros. Illogical, because these will measure current, they will measure voltage, they will do all sorts of things, and they are very, very useful instruments if you know how to use them, if you're doing car electrics or something like that. So, I want to measure amps, so I'll go to the amp setting. Where is the amp setting? I want 10 amps here. Okay, and it should be showing 0, hopefully. I'll switch it on. And what have I got?
50.
50? 49?
0.2.
Thank you, 0.5. There is a world of difference between having 50 euros and 0.5 euros. 0.5. 50 amps, and I probably would be engulfed in flames. Okay, your household circuits go up to about 13 amps, maybe 15 amps for an electric sauna stove. Okay, whoa, it's gone off. How dare you? Right, okay, these are a bit loose.
It went down.
It went down. Yeah, this is 0.5 amps, 0.49. Okay. Now, there are 0.49 amps going through here. If we use our model, energy, electrons are the people go around here, and this is a lovely fantasy land because nobody ever dies, which is really good. So nobody gets stuck. If I measure the current somewhere else, what? Two. 3, a little wall.
How like that? So if you put it like that, it's gonna roll away.
It will do, it's enough, it's enough. Nobody dies on this circuit. What a wonderful world. Actually, would it be wonderful if nobody ever died? Population, yeah. It'd be wonderful if certain people didn't die.
Yes.
Okay, so here, I know I got me red and black's the wrong way round. Doesn't matter. I'm not colour prejudiced. And I turn it on again. Oh, you, I hate you. I love you. Right, bit of encouragement. This is the bit that never works when you use the teeny tiny bulbs. You don't ever get the same reading there as you do there. Down by 0.1, thank you. Okay, same current goes through here as goes through there, as hopefully goes through the last one. The current is never used up.
Is that negative?
Yeah, it's got a very bad attitude.
How can the current be negative?
Because I've got me red and me black. One of these is a positive terminal, one of these is a negative terminal. And I've just got them the wrong way round. That's how it's negative. It's like turning your battery the wrong way round. Okay? Are they all saying 0.49?
Yeah.
Hurrah, miracle, okay? When you've got a large enough voltage, you've got proper bulbs rather than teeny tiny little torch bulbs, then you can actually show this. The current is the same everywhere in a single loop circuit. So there's only one path here. There's only one route for the electrons to go through. Okay? So the current that comes out of the wall, that goes into the lights and goes back into the wall again, it's the same. So when you pay for electricity, you do not pay for the electrical current. Because what goes in comes out. Instead, what you're paying for is what the sweetie shop supplies, which is the energy. You're paying for that, the job that is done in the component. The wasted energy as heat as the electrons go through the wire, which shouldn't be very big, but might be. Okay. Any questions? Now, you are very, very clever people, so I'm not going to lie to you. It isn't one single electron that runs all the way around the circuit and back again, followed by billions and billions and billions of its friends. Instead, it's one electron pushing an electron in the next atom, and then that push goes on and on and on and on and on. Your individual electrons, yeah, they do move a bit, but they don't move massively. Okay? Now, what happens if we give these electrons a choice? And we get to this part here, and we connect up that bit of the circuit. What's going to happen now? Anything. Anything?
Yeah, of course. So depending on what switches are on.
Let's assume that both switches are on.
Well, they both should not necessarily as brightly as.
Both light up, but not necessarily as brightly. Somebody knows his electricity very, very well. Okay. What's happened? Sorry?
They're using energy.
They're both using energy. They've halved the energy. Is that enough to light those feeble bulbs?
Yeah.
No. Let's see what happens if we up.
I don't think the
What
other
do you put the switch? I think the switch.
Yeah, so
This one's different number.
switch is not.
That's a bigger number. That's a bigger number. How do I know that switch is working?
Well, they're both on.
They are actually both on. I know they're both on because look at that.
It shows the
It's halved. Yeah, it's halved. Why? Half of them went that way. Clever. They are actually pretty amazing little electrons. Half of them went down to the bottom. Because they knew this bulb is the same as that, and it's as easy to go down the bottom as it is the top, because they have to do, well, it takes as much energy at the top as it does at the bottom. So let's check. Let's hope these meters do their job properly.
Yeah, if you switch the other switch, would the would all of the energy go then to the other one, even those they are connected?
get too close to current.
Ignore the minus sign. I've got the other way around. The terminals the other way around. These two should be the same. They're nearly the same. It's not as cooperative as I want it to be. It's nearly the same. If I switch that off, 0, these three should be the same. So current is never lost. Okay, and it does divide up so that it's logical. Now, when I put more load, a heavier, a more difficult job onto the battery, by saying, hey, there's 2 bulbs here. What happens to these?
It gets brighter.
They get brighter. I've added bulbs, but it's got brighter.
It's gonna just go somewhere.
We only have one light to be able to provide the image.
Say that again. They've only got,
Like one thing to light up so they don't have to divide into 2.
there's less goes through here, so therefore more can be used up
Yeah.
there and there. I like your logic.
It has to go somewhere. So it's-
Yeah, it has to go somewhere, yeah. These 2 amounts will add up, those 2 energies will add up to the same amount that we've got originally. But it's contrary to logic that if you add more bulbs in the choice patterns, in what's called a parallel circuit, because the current is running parallel here and here, that actually these go up, these get brighter. And it works if I just switch it that way around as well. Okay, so this was a nightmare to put together. It was a nightmare when helped by certain cats. Took a long while. Imagine this is household lighting. Imagine it's even just this room. So we've got the power supply, and then we've got a switch over there. We've got 4 switches. So there's a junction going in, and then there's 4 switches, and there will be a fuse somewhere. And then in the next room, you've got the same again, and you've got the same again. And it gets messy very, very quickly. Real life wiring is very messy. So physicists turn that into nice logical circuit diagrams. Did you do circuit diagrams when you were doing technical work?
Yeah.
Ever?
Yeah.
Did you? Yeah. Okay. So I'm going to turn this into a circuit diagram on the board, and also use these images, these analogies that I have been giving you. Any questions? Yeah.
So why did it happen that then? Because shouldn't they then by logic the 4 of them like all be on the lower light when you have it, but those 2 are brighter, those 2 are on. Like I don't know.
It's horrible, this explanation. It can also be very, very mathematical. The electrons, when they leave the battery, they can see the whole circuit and get a sense of how much energy they've got to use throughout the circuit. Yeah, so they know. It's almost from how it works is actually the electromagnetic forces being passed on around the circuit. So they know they're going to have a certain amount of energy to get through here, even though they've got choices. Because they might just have 2 paths, they might have 10, they might have 20 paths. So if they're 10 or 20, it'd probably be enough to blow these bulbs. Because it'd be very, very, very bright. So they know that they've got to have a certain amount of energy to get to here, and then to get to here and get to there. And the amount of energy that is used in that part of the circuit is going to be different to the amount of energy that's used here, which will also be the same as here. And they divide their energy up equally among each of the branches. Yeah?
Why is it less what they use there?
In each of the branches, from here to here, what have I done there? Yeah, now they're both on. You can see it's less because the bulbs aren't as well lit. Why is it less? They get from here they get to this place where they make a choice. And if each path is equally difficult, yeah, so you've got 1 lamp in one lamp in the other, then they'll do 50-50. If there were 2 lamps in this path, they'd say, hey, that's twice as difficult. and twice as many would go through the bottom. So they make a decision according to what's the resistance of the pathway.
But it's like, are those two together added the same as? Yeah,
No.
why? But isn't it?
I thought.
Excellent timing.
No, I saw that, yeah. It's the end of
Answering really tricky questions. Series and circuit, parallel circuits.
No.
No.
Annika's coming to this.
No,
she's
Let's
coming.
go to today, but sure.
He's gonna be at school tomorrow.
At school tomorrow. The ski day.
Yeah.
So here we have.
There are 4 variables. Okay, they actually all boil down to just 2. There is the current and the voltage supply. The voltage equates to the energy. Okay, and then there is the resistance. And what is happening is that the voltage from here to here has one value. So there's a certain amount of energy used up between here and here, and they're shared equally according to the branches. And the amount of energy depends on the number of lamps. So if there's 1 lamp, actually these 3 parts have equal energy. If there are 2 lamps here, then there is. My brain is not working. There is less energy here, and there's more here, and there's more here. Yeah, of course there's more. They're brighter. Yeah. Yeah.
But why is there more there?
Why is there less there?
Yeah,
Like, is there less when they're on?
Because the resistance of this path is, in total, with the 2 choices, is more difficult than getting from here to here.
Then shouldn't there be more here?
Yes, it
Because
defies logic. It's because of the way that there's something called the voltage is divided up.
but isn't, like, that is equal to this?
Yeah.
Those 2 together.
These 2
Yeah,
are equal.
and those.
That plus that equals that.
Yeah,
Yes.
that's what I was trying to ask.
But that's the current. It's not the energy. The number of. That's a more sensible question. That's a more usual question. Yeah. The current number of people get to here, half of them go that way, half of them go that way.
Yeah.
And then they rejoin. So that plus that equals that.
Yeah,
If I had 8 branches, each with a meter,
Yeah.
each one should be an 1/8 of that.
Yeah.
Yeah?
yes. So
But
then.
from the bulb brightness, you can see that the energy used in each bulb is different.
Yeah.
Yeah. Okay, sorry.
Why is that different if those are the same?
Why is the energy different if the bulbs are the same?
If these are the same.
Because this is not the total energy.
The energy emitted by that. This,
These are the same.
yeah.
Ow! These are
Why
not.
aren't they half of this if those are this?
In the intensity of the light that's given off,
Yeah.
you mean? Because the way that those lights work, it's not a simple case of doubling the current, doubling the light output. Yeah, it rarely is with light. You've got to put a load of energy in before you get anything out, and then suddenly you get a lot more coming through. So for instance, if we wreck our circuit, and I've got the fuse here, if you watch that, okay. Why is that not working? Should have been
Because
working.
the glass is connected. Yeah. Other way.
Duh. Trade me as someone who's got a brain. Thank you. Thank you very, very, very much. Okay. 2 volts.
That black over there is not connected.
Now it's working.
No, it's actually.
Not good, yeah.
Yeah, I want I'm going through the fuse. So I've got a dim light here. I've doubled it, tripled it. I can't say if it doubles in light intensity when I double the voltage that easily, but it usually it's dull for a while and then it goes up quite a lot. Probably haven't got enough control here. Have I answered your question? Tell me the question one more time.
That I don't understand, but why do then, if they have all of the four of them as choices, why don't those light up? And why do these light up more bright? Why don't all of them light up?
Equally bright.
Or these light up like according to the current of this?
So why do the electrons know when they come out? Well, all the electrons have got to go through here.
Yeah.
So they've got no choice but to make that very, very bright. Yeah? The fuse isn't working now. So they've got no choice but to make that bright. They've got no other path. It is. No other.
The amount of energy going through. Yksi noista nousisi ei ole tarpeeksi käydä.
They've got no other choice, they must go through there. And when they rejoin, they must go through here. So they make the decision here 50-50. Yeah? But 50% of the current is not sufficient, it is not enough to light that to any level of brightness.
So then they have to light up a little more.
Because these recombine,
Yeah.
and they end up going through that, and they will use their energy there. Because when they get there, they have to do a certain amount of activity, and that's the result of it.
So if that would be higher, the amount of energy would these then?
Yes.
And would those other ones be?
Yes.
But in normal,
Okay, they are. I can just about see that those are faintly lit. If I put another power supply in, then it would, or a light. They've got a little bit of light there. If I put another power supply in, I could get those to light up even brighter. But the meters, the ammeters, prove that there is electricity going through. Okay.
why do we then have like that kind of like these whatever these are called?
Circuits.
Well, no, these delta things. If it doesn't like work as well as like one circuit.
That is a brilliant question. Yeah, that is a really, really good question. What happens in your whole house lights if you had a series circuit and one of the bulbs then didn't work? If there was a gap here, if that broke.
One broke,
There's no path then for all the electrons to go through, so everything goes off. Yeah? If you switch one light switch, everything else might go on or off as well. Yeah? So actually, you've got two types of circuits. You've got a series circuit, like a TV series, one show after another, they immediately follow on, and then you've got a parallel circuit. And series circuits generally are not very good. They're incredibly simple. If you want to control two things at the same time, it's okay, but two things at a different time, like you don't want your indicator necessarily to be on at the same time as a horn on the bike. And that's what would happen in a series circuit. So parallel circuits are used far more often. It used to be the case that you'd buy a string of old Christmas lights, and they were all in series, and one bulb would blow, and you never knew which one it was. So now they tend to be, actually they're quite cleverly partly in series and partly in parallel. because parallel actually can also be a little bit more dangerous because of the voltage, which we'll talk about next time. So series is much, much riskier. And then you get really complicated series circuits, like a light switch that can be controlled from two, or a light that can be controlled from two different switches. That's quite clever. That really confuses the electrons, but it works quite well.
I have one of those things. I like that it can be controlled by the switches.
Yeah, stair lights normally are like that. And all of them need to have some sort of safety issue in them as well. Okay. Any questions? I could have got you setting all of these up, but it would have been a very, very frustrating lesson because actually when you're using little bulbs, the resistances aren't so good. So think about the sweet shop, the people. The ammeter here counts the number of people each second through a particular point, and the lamps, I don't know, that could be a gym, it could be a swimming pool, it could be anywhere that you're using up energy. Are you eager to get back to the sweet shop supply then? You're eager for your lunch? Okay. Right, I guess we write the notes next week.